Okay, you'll see here 1, 2, 3, 4, 5, 6 of the assignment problems. So we're going to go through these one by one. You can look at them one by one. You can look at all of them. You can leave the video behind and come back when you get to a problem, get stuck. So you can use the video as a way to help you do assignment 12. So here are our two equations that we're well familiar with. This is the definition of torque, and it's how we calculate torque. Three things, right? The distance from the force of the axis, the force itself, and the angle, say it, between the R and the F. Be careful about getting the angle right. And so we're going to use that, but the way we're going to solve the problems is these are all static problems, so they're in equilibrium, so it means the sum of the torques have to be 0. So in this case, we're going to get the sum of the torques to 0. And in some cases, we'll use the fact that also, if it's in equilibrium, the sum of the forces in the x direction have to be 0. Whoops. Sum of the forces in the y direction also have to be 0. Why? Because the object isn't accelerated. It's in equilibrium. It's in a balanced condition. So we're going to start this problem with our sum of the torques equal to 0, and we're going to use this to calculate all the torques. Okay, so we write down sum of the torques equals 0, and what this is telling us to do, it's telling us that on the left-hand side of the equation, we're going to add up all the torques, we're going to set them equal to 0, and then we're going to solve for what we want. But when we apply that to this problem, we look at it, we don't necessarily know what the axis is. Is the axis her center of mass? Is the axis the feet? So the first question in the assignment is, what is the reaction force? So if we want to find this force, and we do know her weight because we're given her mass, but we don't know this force, so we're going to set the axis here. Why are we going to set the axis here? Because then this torque will be 0, and if this is our axis, this will be a negative torque, this will be a positive torque, and those two torques will have to be equal and opposite, and we can get the answer we want. So once again, notice what I'm doing. I'm choosing the axis. And you can do this. So I'm going to write it down. The axis that I've chosen are the feet. So I'm going to calculate the torques about the feet. All right. So pause the video and see if you can write down on the left-hand side of the equation all the torques and then set them equal to 0. And then come back and see if what you wrote down is what I wrote down. Okay, do you have this? Now notice I wrote down there were 3 forces. So I wrote down the torque for each force. We don't always have to do that because this torque is 0. Why is it 0? Because the distance, the R, right, the R in the equation is 0. The distance from the axis to the force is 0. This torque is 0. I put a 0 and I wrote it out. Then the next force is negative, so I put a negative sign. The distance is 0.9 meters. I put that in. The force is the weight of the person, which is going to be mg. I didn't put that in yet. And then the positive torque is the 150 times the reaction force that we're trying to find times the sine of 90. Oh, by the way, the weight, notice the person is flat and the force is straight down. So there should be a sine of 90 degrees here as well because the force is perpendicular to the person. Okay, now finish the algebra, put the numbers in, and solve for the reaction force, and see if you can get the answer that I get. Okay, here's the algebra. I crossed this out because it's 0. I crossed the sine 90 out because it's 1. And then I did the algebra. So this is negative, so when I bring it to the other side of the equation it becomes positive, so 0.9 meters times the weight of the person, the mg, 50 kilograms times 9.8 meters per second squared. Notice I wrote all the units. And so then I have to divide both sides by the 150 meters. And notice that the meters will cancel. I didn't cancel them. And so I'll be left with kilogram meters per second squared, which is a Newton. And so the answer that I got, I forgot to write it down, is 294. So 294 newtons. I can cancel the meters. Okay, so now we have the reaction force, and the next question is, what is the FP? And that P, they're using P because that's P for pivot. I would call it F feet. What's the force on the feet? And so for this, it's easier. We don't need to use the torque equation. The easiest thing is to recognize that there are two up forces and one down force. So the two up forces have to be equal to the down force. So to get the FP, use the sum of the forces along y, the sum of the forces in the y direction, equal MAY equals 0. So write that down and see if you can get the answer that I get. Okay, pretty straightforward. Sum of the forces in the y direction equal MAY. In equilibrium, they equal 0. So I wrote down the three forces, two positives, one negative. I did the algebra. Notice the method. And so FP equals the weight minus the reaction force. The weight is mg, 490, minus the 294, and we get 196. Okay, now the second part of the problem is something that we used to do in lab, where we use the same figure. So you go to the lab and you stand on the scale. Let's say this woman was doing it. She would read her mass at 50 kilograms, or if it was a Newton scale, it would read 490 newtons. That would give us her weight. And then she would put her hands, she'd put her feet on the floor and her hands on a bathroom scale, and that would measure the reaction force. And so in this case, we know her weight and we know the reaction force, but what we don't know, you see this 90 centimeters? Notice that we were given that, and 90 centimeters is not half of 150 meters, or her height, which isn't given. So your center of mass isn't necessarily in the middle of your body. You might be top heavy, you might be bottom heavy. So in this case, we're given it, but then in the lab example, we're going to find, so we're looking for this distance. That's what we're trying to find. So use the same equation with the information given, and let's find this distance, the distance from the bottom of your feet to the center of mass. So try that and then come back and see if you did it right. Okay, I think we're done. So here's the equation. Sum of the torques equals 0. Always start with that equation and indicate your axis. I put the feet. And so then I wrote the torques. So I wrote this torque is 0. The next torque is here and it's negative. That's important. And then the last torque is, I called it x hands, the distance from the feet to the hands, times the scale reading, the reaction reading. Now we have a scale, and set all that equal to 0, and then solve it algebraically. So x of the center of mass is going to be x hands times the scale force divided by the weight. I left this in centimeters. There's the scale force it's given. There's the weight it's given. And so we get an XCM of 93.6 centimeters. Oops, I forgot the units. And then it asks to find out the percentage of the total height. You can see that the total height is 180. This is a little bit more than 90. So this person's center of mass is slightly above their midpoint. And so we get a fraction of 0.522, or 52% from the floor to where their center of mass is of their total height. Okay, let's go to the next problem. Okay, I think we can speed up now. So here's the next problem. It's an arm holding a ball, and so you can see the anatomy here. And so there's the person's holding a weight, which is a force down, and there's an elbow joint. So this is a natural axis, right? And also there is a force at this axis, at the elbow joint, that we don't know. That's the E for elbow. So this is what we're going to use for our axis. So when we use our torque equation, we're going to have this be the axis. And so there'll be one force here. And then the thing that causes the arm to lift is this tendon in the bicep muscle. Okay? And in this case, we're ignoring the weight of the arm, which is not really a good idea. In the next problem, we'll account for it. But in this problem, there's just two torques, three forces. Remember, there's a force at the elbow, but the force at the elbow doesn't cause a torque. So write your torque equation and see if you can solve for T. Okay, so you want to practice writing out the equation and doing the general solution, practicing this algebra. So just follow what I did. I set the torques equal to 0. I said the torque's about the elbow, and there's two of them. So this is a number, so I gave it a name. I called it R for the tension force, and I called this R for the weight force, rather than write the numbers in. So the R, the F, and the sine of theta, right? For each one I'm doing an R, an F, and a sine theta, minus the other R, that's the 13 centimeters, times the weight, the 50 pounds, times the sine of that angle. And then I did the algebra, and I got this. This factor goes over there, and then I divide by RT, and I divide by sine of theta t. And so there's the 13 centimeters, there's the 50 pounds. And notice this is a little tricky. The forearm is this way, and the force is down, and so it's the angle between here and there. So there's from here down to here ends up being 120 degrees. Right, it's going to be 60 degrees here plus, wait a minute. Yeah, this is 60 degrees here, right? So the angle between the tension force in the arm is 60 degrees. So that leaves this 30 plus 90. If you bother to do that, that's 120. And so when you do this, you get 433 pounds, or 1927 rounded to 1930 newtons. So it's worth noticing that the tension in the bicep muscle and this tendon is more than 8 times greater than the weight you're lifting. So this is why tendons are subject to very high forces. And why is it? Because the tendon is close to the hinge, the elbow. So the tension force has to be much, much greater than the force that you're lifting. And this is often an issue in sports physiology and physical therapy. So we'll see some more examples of this. Okay, now the last thing is to find the elbow force. And we'll do the same thing we did last time, do some of the forces in the y direction. Okay, so here's the equation. There's the tension force up, the weight down, and the elbow force. And when I solve for the elbow force, I see that it's, I see that it's negative. It's important that it's negative. Yes, the elbow force is down. So the elbow's exerting a force down on the elbow joint, and also a pretty big force. So that's why there's a lot of stress in this joint when you're doing weightlifting. Okay, next problem. Okay, here's the next problem. It just occurred to me that when we do these problems, we have a system or a series of steps that we're following. And I hadn't really mentioned that or reminded you about that. So think about it, pause the video and see if you can remember what those steps are that we use in solving force and torque problems. So here are the steps. You'll find them on your equation sheet. And I've really just been starting here and doing this. But we should have a diagram and a free body diagram, which we do. So if you see this one, we have the diagram and it has the forces in it. And then we have the free body diagram, which is just a schematic of the forearm showing the forces acting. And then from here, we use our equation. So we're going to go back to this. Here's our diagram. Here's our free body diagram. And we're going to do some of the torques to find the force of the bicep muscle. So pause the video and see if you can write that equation out, do the algebra, and get the answer. And then once you're done, come back. Okay, here it is. So a couple of reminders. Every problem in this, I think, probably every problem was going to start with this sum of the torque equations. Because it's static equilibrium, the torques are going to equal 0. And every problem you should look at it and have a good physical sense of what's going on. So if you look at the arm, you have one torque by the bicep muscle, and that's torquing the arm positive, and two negative torques. The arm would fall this way if it weren't for the bicep muscle, and you can see that in the free body diagram. So I know that this bicep torque is going to have to be equal and opposite to these two negative torques. Okay, so here's the equation. I wrote down every torque. The force of the elbow is 0 torque because R is 0. For every other one, I'm writing, right, RF sine theta. So here's R1, force of the bicep muscle, sine of 90 degrees. I didn't want to write it out, so I just put in a 1. But don't forget, you've got three things, R, F, and the sine of the angle. The next one is negative, so I put in a negative sign. R2, the weight of the arm, times the sine of 90. The next one's negative, R3, weight of the book, sine of 90, all equals 0. And so you can see if I take this term, if I take these two negative terms and add them to the opposite side of the equation, I'm going to get this. I'm going to get that this torque is equal to these two torques. Well, I did another step of algebra, right? I took the R1 and I divided it across, and so there's the answer. We can calculate it, but we like to simplify it. Like if you go to calculate this, you're going to put G in twice. It's actually much easier to calculate if you factor the G out. So here we factored the G out, and this is what we get. And if you go to the next problem where you're identifying these generalized equations, you'll see this equation as the one for the force of the bicep muscle. So this is the generalized equation, put the numbers in, and get the actual answer. Okay, now we want to find the force at the elbow. So for that, we're not going to do another torque equation. We could change the axis to here or someplace. But we're just going to, there are only y forces, right? So do sum of the forces in the y direction and get a generalized expression for the force of the elbow. Then come back. Okay, there it is. Sum of the forces in the y direction. No x forces. There's only one up and there's 3 down. And when you do the algebra, you get this equation, and you can find that equation in the next problem, and you can use this equation to do the calculation. All right, let's do the knee problem. For some reason I couldn't find the whole figure. I just got this piece, but I drew out the knee, and at the top of the femur muscle at the top of the leg torques the knee this way about the joint, so it pulls this way, which is going to lift the knee, and some counterweight of 10 kilograms is put here to make it so that the person has to use more force in this muscle to counteract this torque this way. So this is a positive torque, right? It's lifting the knee. This is a negative torque. It's twisting it back. And here's the free body diagram that shows the knee joint, the force of the femur muscle, and the tension muscle of this weight that you can see in the figure in Moodle of the 10 kilogram weight. So the tension force is going to be 10 kilograms times G. So pause the video and write the torque equation. Okay, I hope you paused the video. So there's the torques, and I'm calculating the torques about the pivot. And you see there's two of them. There's a positive one, and I'm using the symbols from the diagram, the R perpendicular prime times the force of the muscle. There's the sine of 90 degrees, which is 1. And here's the negative torque. Okay. And I set them equal to 0. And then when I solve for the muscle force, this is the equation. The tension is mg. And then in order to get the force of the knee, that third force, you can see both forces are negative, so that third force has to be positive. When we do sum of the forces along x, you'll see there's a positive force equal to those two negative forces added together. All right, so very similar to that problem is the foot problem. And you can see that there are three forces, and the foot is simplified down so it's just like a straight bar. The three forces are acting through this bar, and the middle force is the force at the ankle joint. So the normal force at the tip of the foot is equal to the weight of the person. Imagine yourself standing on a scale on the tip of your foot. The scale would read your weight. So the scale is pushing up on you with a normal force equal to your weight. In order to lift your heel, you had to pull up with your leg muscle through the Achilles tendon, lifting the foot up as it rotates around the ankle joint. So we want to write the torque equation about the ankle joint. You can see there's two torques. That's a negative torque, and it torques it that way, and the normal force is a positive torque because it torques it counterclockwise. So go ahead, write that torque equation, and then come back. And you can see the foot bone is pushing down on the shin bone is pushing down on the foot, so that force is down and equal and opposite to the two forces going up. So this is very similar to the last problem. I think you can handle it on your own. So write those equations and try and solve it. So here's the next one. Not that different, actually. A straight horizontal bar with a number of forces acting. So draw a free body diagram down below and pause the video and come back. Draw the free body diagram of the bar showing all the forces. Okay, if you drew this, you've missed two. Pause the video again and go back and take another look. There they are. The force at the pivot up and the weight of the stick itself. So you can see there are 4 down forces and 1 up force. So that force of the pivot has to be equal to the sum of the 4 down forces. That's what you'll get in this. That's what you're going to do in the second part of the problem. But in order to find M3, which isn't given, all the other masses are given, you're going to have to do, the first thing you're going to have to do is sum of the torques about the pivot in order to find mass 3. So that's your axis, and you have to measure everything. All those other forces have to be measured from the axis to each force when you calculate the torques. So make sure you do that correctly. those three are positive torques, and the M3 is the negative torque. So the one negative torque has to eat the three positive torques. So hopefully you were able to write the equation. You see there's the four torques. R3, M3G, that's the force, and then 1, the sine of 90 degrees. And then the other three torques are the negative torques on the other side. M1, M2, mass of the stick, and the distances to those forces. So when you do the algebra, you get this simple expression for M3. Why? Because the g's all canceled out. Notice every term has a g, and so you can divide by g. It goes out of the equation. You got to be careful about what R1, R2, and R stick is, right? R2 is 40 centimeters, R3 is 30, but the mass, the force of the stick is at the center, so the distance from the pivot to the center of the stick is 20 centimeters. So you got to be sure to get those distances correct. Okay, the last thing is you need to get the pivot force, right? So you're trying to get the force of the pivot. You have to realize that the one force up at the pivot is going to be equal to the three forces going down. Okay, skipping over a couple problems, we're going on to the crane. So here's the crane. So the diagram is given with the various angles, and now we need a free body diagram. So pause the video and draw a free body diagram of the boom of the crane. Okay, your free body diagram should look like this. This line is the boom. There are four forces. There's the weight of the load that acts at the end. There's the tension force from the cable attached to the end. There's the weight of the boom straight down, which acts at the middle of the boom, since the mass is uniformly distributed. And there's a force at the axle. And thinking about the situation, we realize that the force at the axle has to be equal and opposite to this force, and the y component of this force. And it has to be equal, its x component has to be equal to this. So it has to have a positive x component, a fairly large positive x component, and a fairly large positive y component. So I just draw it randomly in that direction. But first we got to get the force of the tension. For that we're going to use some of the torques about the axis. So pause the video and write your torque equation for the sum of the torques about the axis. Okay, there's the equation. Sum of the torques equals 0. So the first torque, the positive torque, acts at the end of the beam, so it's a distance L, the length of the boom. There's the Ft, and there's the sine of 10 degrees, the angle between those two vectors. That's a positive torque. The first negative torque is the weight of the load. That acts at a distance L from the axis, and the angle is 60 degrees, right? Because it's this angle, it's not this angle. And then the weight of the load acts at a distance L over 2. So there's the weight of the boom. That's the mass of the boom times g. And that also acts at an angle of 60 degrees. All that's equal to 0. Notice, like in previous problems where we could divide by g, every term has an L in it. And so the L's, if you divide by L, it'll cancel out. You don't need it in the final expression. So I'm going to let you do the algebra. You need to solve for Ft. I think you can handle that. And then once that's done, you need to find the force at the axle. And you're going to have to do that in two parts because it has an x part and a y part. So when you get to that, make sure that you use sum of the forces x equal to 0 to find the x component of the axial force, and sum of the forces in the y direction equal to 0 to find its y component. And that should take care of the crane problem. Okay, let me get you started on the latter problem, the last problem. And what we want to get is the generalized solutions, the general equation solutions. With that, we can certainly get the answers for the numerical answers. So once again, here's our diagram. You need to draw a free body diagram. We'll do this for just any generic ladder of length L and any angle theta. We have a specific one here, but make the free body diagram just L and theta. Okay, pause the video and do that before you come back. Okay, sum of the torques equals 0. There's two torques. The positive one is this one. So the distance to the axis is L. The force itself is the normal force of the wall. And the angle is the sine of theta. You can see that's the same angle, theta. The negative torque acts at L over 2. It's the weight of the ladder. And it's the sine of 90 minus theta. But in this case, there's a trick you might not think of. The sine of 90 minus theta is equal to the cosine of theta. So it will serve us better to change that sine of 90 minus theta so we just have one angle. The other thing is, notice like the last problem, you can divide both sides by L. And so all you need now is to solve for the normal force of the ladder. And then, as we did in the last problem, you're going to do sum of the forces in the x direction and sum of the forces in the y direction. And you should be able to come up with the equations and the answers and the numerical solutions to this problem.